from various institutions and needs that you perceive for the sea ice outlook or your predictions, and then your vision about how the sea ice outlook should change. So not every talk may get all 3 of those topics, but that was the general idea. We have 10 talks, so we've asked everyone to give their talk in 8 minutes, and Betsy is going to keep time, and she's going to show you a 4-minute and a 2-minute warning. No, sorry, just a 4-minute. And then a 1-minute, is that right? And then I think she's going to stand up at 30 seconds. She's pretty intimidating, so careful there. And so we will try to keep you to 8 minutes. And I think if we're actually on time after 5 talks, we'll pause for a discussion because we would be able to finish quite comfortably if everyone is on time in the hour and 20 minutes that we have. Does that make sense? Well, 120 minutes. Yes. Excellent. Okay, and just for simplicity, we're going to go in order that I had on the agenda. So Richard Cullether is first. And I think, if you don't mind, use this.
And what do I do to the buttons? Okay, hello. My name is Richard Cullether, and I'm here with my colleague Bin Zhao, and we're with the NASA Global Modeling and Assimilation Office. The reasons why we're here is that we use our relative objectives of using NASA observations and data assimilation to improve climate models and contribute model integrations to the National Multi-Model Ensemble predictions and international assessments. And so seasonal forecasts tend to come under those objectives. We do other things for polar research. We produce MERA, which is the NASA reanalysis. We're working on the upcoming MERA 2, which will begin production shortly and will take a couple of years to get up to real time. We do other things. We collaborate with the NASA Cryospheric Science Laboratory on modeling. We are also in a Goddard center-wide interdisciplinary focus on Arctic boreal systems. And we contribute to the North American Multi-Model Ensemble, which I'll talk about in a second. So our model is the GEOS 5. That's our special sauce, is our atmospheric general circulation model. We couple it with the MOM 4 at a ½ degree resolution and CICE to produce our seasonal forecasts. We routinely produce seasonal forecasts, which are then disseminated to the National Multi-Model Ensemble. This is a setup of how we do our assimilation, and then it proceeds on to a forecast. And so this is some examples of some of the forecast products we produce. We produce Nino plumes, and as you can see, we're forecasting in El Nino, and many other groups are also forecasting warmer SSTs in the coming months. These are some examples of our data assimilation for our sea ice. So we use the model to produce an analysis increment, which can then be used to force the model towards the observed sea ice extent. We do not assimilate sea ice thickness, and as you can see, we have some difficulty in keeping thick ice in the basin. And so this is the last year we submitted for the first time to the Sea Ice Outlook. So as part of the National Multi-Model Ensemble, we produce an ensemble every 5 days, and then at the end of the month, we run an ensemble of 10, so there's about 16 members that go into a monthly forecast. And as you can see, we produced a low forecast. I didn't normalize it when I submitted the forecast, so there are differences in the landmass that are associated with these forecasts. I was nervous about normalizing, and I think that's an issue that could be discussed a little bit further. I don't think it's a trivial question. As you can see, we forecast thicker or more extensive ice recovery in the Beaufort Sea, and if you compare to observations, I didn't think we were doing that badly, and so I thought that there was some reason for optimism in doing this. This was our sensitivity experiment that Ed described this morning. I don't think I'll go into that. Oh, except to say that this was the first time that we varied the sea ice thickness. We don't normally vary the sea ice thickness in our ensemble forecast or the sea ice extent. So each of our ensemble members uses the exact same sea ice extent and thickness. And so in the future, because we developed it specifically for this experiment, we'll consider incorporating that into our multi-model ensemble. So again, our near-term objectives are to produce MERIT-2, and we also wish to incorporate other observations into our ocean data assimilation, GRACE and Aquarius. We're hoping to get out of this just incremental improvements in our forecasting system. We use this this is a motivation for us to look at our Arctic and sea ice forecasts. We normally don't look at those. We produce Nino plumes. And so this was a motivation for us to look at that. We assume that other groups that produce modeling forecasts for the sea ice outlook are submitting them based on their submissions to the National Multi-Model Ensemble. We could be wrong about that, but we think that that's probably for many other groups. That's where they're submitting their forecasts. So we would suggest that you guys put a lasso around this group, which is with NOAA, to obtain forecasts, and perhaps it could be used to set up a MIP type experiment. That's it.
How much time did he have left? Come on. If he has more, like a minute, we could take a question. Oh, well, take a question then. A what? What was the question?
NMME is the National Multi-Model Ensemble. So that's a project that's run by NOAA it's to produce a multi-model ensemble of the seasonal forecast. So they produce a 1 to 3 month seasonal forecast of temperature and precipitation, both globally, and they center on North America. If you Google NMME, you'll find this right away. I think it's the #1 thing. There's also an international multi-model ensemble. I think that's associated with EuroSIP. I have to confess I don't know too much about that.
Do you want to take one more question from Janet?
Okay, go ahead.
I was just wondering, does NMME have a process or a specific planning mechanism that they would look at sea ice as a particular sub-project?
Yeah, I don't think sea ice is any part of the forecast. So I think, please do.
So as part of the Earth System Prediction Capability effort that was going on, they did ask us for input about what sea ice fields they wanted to output, and we did give them some recommendations. I don't think they implemented very many of them. So I suspect what you're going to get out is the usual sort of sea ice extent and those sorts of things. We asked for kind of full budget analysis, but I don't think they had the capability of doing all of that. So they have asked for input from various groups.
I would add there's other groups that contribute to the NMME that haven't provided sea ice forecasts for the sea ice outlook, including NCAR. So that might be something to pursue in the future. I asked Rick about this, and she said, "What is NMME?" And I think somebody at NCAR should talk to Joe Trivia.
All right, thanks, Richard. Obviously, that was really important conversation. We should continue, but we'll carry on now with Nevin Fuchkar from IC3, which I think is a really neat name. I'm sure he's going to explain how it came about.
Hi, can you hear me well? All right, I'm Nevin Fuchkar. I'm from IC3, that is Catalan Institute of Climate Sciences in Barcelona. I work in a climate forecasting unit led by Francisco Dobles Reyes, Paco. Specifically, we are working on Polar Climate Prediction Research Line, which is led by Regina Guemas, and she sends her greetings and apology that she could not join this workshop, although she was very interested about it, and if she's watching, hi. Okay, of course, there are other members. Danila is working on her PhD, and we have two software engineers, Asif Oriol. Well, you can see this nice picture of Barcelona, but what is also interesting for this, I had a really long flight from Frankfurt to San Francisco yesterday, and fortunately I was in good position. I woke up right in time when plane was flying over the Baffin Bay, and this was actually in the Davis Strait, and you can already see start developments of the cracks, and there's another photo. Well, of course, this was with the cell phone, not the real camera, but I was surprised actually you can see some interesting stuff here. Okay, let's go. And okay, so we have two projects that are focusing on climate prediction in the Arctic region and connection with lower latitudes. The projects are, first one is Pika Ice, funded by the Spanish government, and the second one is SPEX. This is FP7 project funded by European Commission. There are several key objectives. First, in Pika Ice, the number one focus in production of assembled sea ice reconstructions. And we're trying to cover as wide period as possible. So there's actually, we have a sea ice reconstruction starting in 1958. And we use this sea ice reconstruction as observational-based states for sea ice initialization. Then a second element of this project is development of new classification tools for study of seasonal and longer predictability, determining the mechanisms from the point of view of a cluster analysis and some other tools. Then our workhorse is ECRF 2 and 3. So we are looking into how ECRF can forecast the sea ice cover, and specifically how well it can forecast these modes that are predicted from a classification analysis. And then the fourth objective is extreme sensitivity experiment, but what we're going to focus is change on a pan-Arctic scale, a regional scale, and what is the new twist is we're going to look at the ocean atmosphere base state at the end of the 21st century. So we're not going to just focus on the present state. We are seeing how, with the global warming progress, in what state we're going to have to decipher the time scale of recovery and other things, but in having a difference from what was being done so far. For the SPEC specifically, it's basically seasonal to decadal prediction project, and there is a component, the work package 3, that looks into the role of sea ice memory, how much it's important to have a observationally based sea ice conditions, and we are coordinating multimodal study, and we're going to talk about it during this workshop more with the collaborators. And Danila, she's finishing her PhD, and she was looking into the interesting differences between full field and anomaly initialization, and she found out that actually there is improvement when you switch from full field to anomaly initialization in sea ice conditions. You have some relevant improvements in your predictive skill. A little bit more, this is, for example, how the development of the observationally based sea ice conditions for initialization benefits. So this is a first comparison root mean square error of the 5 members. The red line is just CMIP 5 hindcast, and then the blue line is using some of the ECRF IC3 reconstruction data, and as you can see that in the beginning there is not much of a difference, but as the forecast time evolves you can clearly see improvement that the realistic more realistic sea ice conditions does matter. Thin lines, this is the sea ice area, and this is Arctic sea ice temperature. The full line and dots are just the different observational based data sets, but again we see improvement in Arctic, both in RMSE and anomaly correlation skills. All right, and then, for example, what is interesting, we are looking at the classification methods, and one of them is K-mean cluster analysis, where the aim is there's lots of methodology and different options, but the essence of the approach is to construct the clusters within which the variance between elements is minimized and the variance between the different clusters is maximized, and they do not match EOF patterns. Also, you have several other approaches. This specific, I'm showing results from our sea ice reconstruction for the sea ice concentration and thickness, and you can see that actually these clusters, they are based on Well, there are different methods. A K-mean cluster analysis is computationally very demanding, so you typically reduce the number of degrees of freedom, and what is typically being done is you do EONF analysis to reduce degrees of freedom. Here we use the projection, you use the self-organizing maps, where you project from your initial space of data into the space of neural network nodes, but you preserve the topological relation between the data. So this has no any EOF constriction in that. There are also other options where you can use a large-scale averages for reduction of data analysis. And here, specifically, how we can contribute from Barcelona is, except this another lovely shot of Barcelona, and this is actually where the institute is located. It's about 5 minutes walk from Bogatel Beach. And we think that we can be constructive in a sense for the outlook is to have ECRF 2.3 predictions. But also we are hoping that we're going to have a seasonal prediction with ECRF3. There's some tuning issues that needs to be resolved, but intermediate version 3.1 should be available in the summer, and it will be very nice to have a contribution from 2 different generations of the model development line. This is more another focus picture on the Davis Strait from yesterday. And okay, of course, if you are interested in visiting Barcelona, please let us know at any time. But perhaps the very good opportunity would be Polar Prediction Project workshop organized in Barcelona, December 10 to 12. Where we're going to talk about the linkages and connections between the polar latitude processes and mid-latitudes and even tropics. So basically, please, if you're interested, contact us, and now I'm open for questions.
One question, please. Maybe. I have one. Tell us a little bit more about spec or specs.
It is a project
Use your mic.
that works on improving the seasonal predictable.
Microphone.
Oh, sorry. The goal is to improve seasonal to decadal predictions by identifying most promising and sources of predictability and where we can make a significant improvements. There are many different packages, from improving the boundary conditions to forcing fields, but specifically, like, we believe that bringing initial condition closer to observations provide particularly promising way to improve the predictions. The point is that is mixed bag, because for certain, variables in certain regions, you can have a predictability up to 5-6 years, while in certain regions, of course, you lose it after 2 or 3 months. But anyway, we are in part of it. We are working on ocean state, sea ice state, and soil moisture, and I'm particularly focusing on observationally based sea ice conditions. How, if we improve them, how much that will be an improvement into the forecast. All right. Thank you.
Hi everybody, so my name is Reem Sadek. I work at GFDL NOAA, so I don't have a nice picture because I live in Princeton, so it's not as exciting as Barcelona or Boulder, but I have a nice picture of a model because we have exciting models. Okay, so I'm actually not a sea ice person originally. I came into this very recently, and so I've been working with Gabriel Vecchi and Mike Winton, and actually we submitted our first outlook, our forecast last year for 2013, and as Richard was mentioning, we're part of this North American ensemble, NMME, and we thought, okay, we have these models, we produce this forecast every month, so it would be a shame to not participate, but we didn't have like a critical mass of people to do it, so I volunteered to do that. And so when we submitted our forecast first, I think for the July report, I really freaked out originally because we were like clearly an outlier here. Like everybody was kind of predicting like a decrease, a loss of sea ice, and we were there the first time and predicting like an increase. And so I thought that people will jump on saying that the NOAA forecast is the only one who's like really an outlier there. And we ended up doing not so bad at the end, but it's always easy once it's done to say, oh, we were right, we're the best, we almost won there. And so you will hear some people from GFDL maybe say that, but I won't say it. And so so we were comparing to like observation. We ended up like 2 too high, but if you take the range of uncertainty we provided there, the observation lay there. So then it motivated more interesting things to try to assess the forecast scale of the whole model of this prediction. And I don't have the answer to say why that particular year validated well, but I show some results about the model we used and how it does in terms of prediction scale. So the model used for that is a CM 2.1 model. So it has a 1 degree ocean, 2 degree atmosphere. We have the sea ice model developed by Mike Winton quite a few years ago with the 5 category of ice. And so we run, I focus on this model, we run forecasts every month. The first of every month we run a 1 year forecast, so we have this quite many initial conditions. And we have 10-member ensemble, and the way we initialize our forecast, so it's fully coupled, ocean, ice, atmosphere, and we have an ensemble coupled data assimilation based on the Kalman filter. And so we initialize our model the first of every month, and we don't initialize explicitly concentration or thickness. We initialize thickness, and with Argo data of sea surface temperature, we actually initialize the extent over there. And in parallel of that model, we have a new model that has the same ocean and sea ice, but it has a higher resolution atmosphere, like 50 kilometer cubed atmosphere. And we are running exactly the same set of experiments with that model. And my motivation was to see what's the impact of a better model, a better atmospheric resolution, on the scale of sea ice at these time scales. And so just quickly to validate this initial condition, I'm not sure the color shows well, the dashed line. This is basically the comparison of NSIDC on the left here with our data assimilation product, so our initial condition, and it shows that we are able to reproduce the seasonal cycle quite well, which you would expect if you assimilate the data there, but we underestimate a bit the extent, and it's less true for the area. And I only showed 2 different climatology to show that between 82 2001 and the last decade, we do simulate well the decrease of extent, but with a shift, so not exactly as observation. And these are September and March anomaly in our assimilation system, and we're doing quite a good job and less of a good job over the last 10 years when the thickness decreased in observation. These are the 2 models, so the low resolution and the high resolution atmosphere, same ocean, sea ice, and initial condition. And basically, they have quite many different features for the atmosphere, but for the sea ice, we have better sea ice concentration in the high resolution model and thicker ice. Both models are too thin, but that one is really like among the thin models. And so does that have an impact on the forecast? First, because when you initialize a coupled model with an ensemble data assimilation, because the model has drift, as with lead time, the model is going to tend to drift toward its own mean state, and that's a really big issue. So we correct the forecast by removing that drift as a function of lead time, but there's no perfect way to do it. And here I'm showing the mean state of these 2 models compared to observations. So observations are in black, and the red model is a higher resolution atmosphere, and the blue one is our low resolution. And the high resolution atmosphere basically has a very good mean state and very good sea ice seasonal cycle. Whether the low resolution ocean has underestimate the summer sea ice extent and overestimate the winter one. And that has an impact on the way the forecasts evolve with lead time, as I'm showing here on this bottom figure, left and right. And this is in color show how the forecasts evolve with lead time in the low resolution ocean. And if you just focus in summer, basically with lead time, as lead time increases and you go down here, we tend to go toward the model mean state, so toward low extent in summer in this model and toward higher in winter. Whether for the high resolution model, because we don't have that drift, there is no real evolution of the drift with time. Okay, what's the impact now? I might go directly to this plot first. And so if we measure the correlation scale now for these 2 models, they have quite high scale. Higher than I think what any other dynamical model have published so far. So this is correlation scale for detrended sea ice extent, and this is the target month and the initial month. So if you want to predict September, this is September initialized in September, and then you go toward longer lead time. And if there's a dot, it means it's significant at 95%. And so we see that we have quite high skill in summer and fall, with some also reemergence in the spring, actually. And what surprised me is these models have quite different mean state, but actually they have very similar skill. This is the high resolution one. And if you look at the September to November, they have like almost the same skill. And the differences arise more at longer lead time, but both models show very good skill in predicting summer and fall. And the differences are actually more visible if we might talk about metrics and way to evaluate the forecast. Yeah, I'm done. And another way is to look at this mean square skill score, which is basically a function of both conditional bias and the correlation. And so a higher skill score tells you that you can have either a higher correlation or also a smaller conditional bias. And if you just focus on the upper part of this panel, it's more blue here than it is here, which means in the high resolution model for spring, winter at longer lead time, you have a smaller conditional bias actually. But for the forecast, for the two models to show an impact, to manifest an impact on the correlation skill or on the forecast skill, 12 months is actually short. So at least in this forecast system, so I was quite surprised to see that the two models have about the same skill. So I'll leave my conclusion here saying, one thing I didn't have time to mention is we have better skill in the 90s and in the 2000s in this model, and I think this is something that's found in many dynamical models, both because we have better observation in the late part of the decade and also because the ice is thinner, but there is overall quite good skill and it's comparable to things that have been published by a few papers recently, so it's encouraging. Thank you.
Thanks, that was fantastic. I have lots of questions, but I think we're gonna go straight forward and here, we'll take that. And is it Felix that's next? He's getting up, so, oh, sorry. Well, we'll go with Felix next since he's up, and Wisla, you'll go next then. Okay, but I have to get your talk up. Do you recognize it? Is it that one? No, it's that one. No, oh, I don't have it queued. Sorry. There it is. Okay.
So, hi, my name is Felix. I'm from Hamburg, Germany, and I work there at MPI for Meteorology together with Dirk Notz and Wolfgang Müller. And I will now give a short, brief overview of our work with the seasonal prediction system based on the Max Planck Institute Earth System Model. And then I will briefly introduce the new sea ice concentration data set produced by the Climate Change Initiative from the European Space Agency. And so the seasonal prediction system based on the MPI ESM model forms more or less the German contribution to, on the one hand, the EU project SPECS, which Neven already introduced, and then to the operational multi-model ensemble EuroSIP. And as I'm responsible for the contribution, for our contribution to SPECS, I will focus in the next slides more on this, or only on this contribution. So what we did was we used the MPI ESM model in the low resolution configuration, so-called LR configuration. This used the atmospheric component ECAM6 with 47 layers and a lit at 0.01 hectopascal and T63 horizontal resolution. And as an oceanic component, it uses the Max Planck Institute Ocean model with 40 levels and 1.5 degree horizontal resolution. And then with this system, we performed an assimilation run from 1979 to 2012. And for nudging in this assimilation run, we used in the atmosphere ERA interim reanalysis data. In the ocean, we used ORA S4 data. And for the sea ice concentration, we used NSIDC NASA team data, and we didn't nudge sea ice thickness or other things there. And then we are currently performing 2 sets of hindcast simulations with 10 ensemble members each, started at 1st of May, 1st of August, and 1st of November every year in the period 1991 to 2012. And one set of hindcasts is initialized from this assimilation run, while the other set of hindcasts is initialized from a climatology for sea ice concentrations. And we performed these hindcast simulations for 4 years already, and I will show here briefly some results for the year 2007. So what you see here in the gray lines here indicate the actual data, the NSIDC data we use for the nudging of the assimilation run, while the black lines show the assimilation run itself. So the solid lines always indicate the actual values in the year 2007, while the dashed lines indicate the climatology. And what we see here is that the model sort of doesn't really agree to the amount of sea ice concentration we give it, because it always, it's not able to stay stable at these larger sea ice concentration values. So, and then in the red lines here indicate the hindcast started from 1st of May, so roughly here, and the blue lines indicate the hindcast simulations started from at 1st of August here. And what we see is that, strangely, the prediction is better if we start on 1st of May as if we start on 1st of August, or at least more close to the assimilation run. And but this is probably related to an issue we found in the initialization of the sea ice concentration in the model very recently. So we will repeat that, but this is the actual status of our work at the moment. So I now come to the second part, and so there is a new sea ice concentration data set which was compiled by the Climate Change Initiative from ESA, and the essential thing, or the most important thing of this data set probably is that it contains information on the uncertainty. And there are different parameters in the dataset which do that. So, for example, we have here the total uncertainty, the gridding, and plus algorithm uncertainty. Then we have a status flag, which indicates for each grid cell the quality of the actual data. So we have, for example, maybe you can see here we have at the coastlines we have different status flags as in the Arctic Ocean, for example, because the algorithm produce more reliable values there. And we have, for example, also the so-called off-range ice concentration, where all the ice concentration values which came out of the algorithm are included, which lie above 100%, indicated here by the yellowish and reddish colors, or which lie below 0%, so indicated here by the bluish grid cells. So this, for example, if you plan to do an assimilation run, this could be valuable information, because then you can try to force the model, or to nudge the model in some grid cells more closely to the observations, and some grid cells less closely. So with this, this yields potential to improve the quality of the assimilation run, I would say. So yeah, these are some more details on the data set. So this was produced, as I said, by the ESA Sea Ice project. There's a web page of this project also, and we have available time series for 1991 until 2011, and this is already available. And then coming soon, there is a sea ice thickness data set for the Arctic freezing season from October to March, covering 2003 to 2012. And this is the web interface to access the data. And if you want to know more about the data set, you can either, or you should feel welcome to contact Stefan Kern, our colleague from University of Hamburg, and or if you're interested in a workshop in September 2014, there will be an international sea ice concentration and thickness intercomparison and evaluation workshop at our institute in Hamburg, Germany. Yeah, thanks.
The 5 talk point. So we'll take one question first just for Felix, and then we'll open it up to a discussion for all 5 speakers. Okay?
Yeah, just to say that I think it's great that you provide uncertainties along with the products. I'm talking here from the data assimilation perspective, where the uncertainties are extremely valuable. I have a question more about the operational side. Do you plan to extend the time period of products up to real time? Because in this case it stops in 2011, so is there a plan to from the ESA to be able to process this data in real time, or it's not feasible?
I would suggest to contact Stefan Kern also for this question. I don't know that. I'm sorry.
So we'll definitely have time, about 20 minutes. Yeah.
As far as I know, the ESA CCI is not designed for recent observations. It's to get data sets for climate research. So yeah, but not for recent times. So it's there will not be an update as far as I know.
Brandon and Francois. Follow my own rules and use the microphone. Are there direct questions for the speakers? And if not, we can probably open it up to some more generic questions like, do you have recommendations specifically for how we could do model intercomparison or Outlook activities that would be applicable to the goals you're working on? Okay.
Thank you. I mean, just looking across all the models that have participated there, I mean, there's a whole range of start dates and so on. I wonder whether there might be some discussion about coordinating particular start dates that we're interested in to more directly compare these models and see at what lead times we may have useful skill in across the models. So, I mean, for example, the MPI model started on the 1st of August and the 1st of May, and I wonder whether there's opportunity to fill in the gaps and do June and July as well, for example.
Yeah, so this 1st of May and 1st of August, these are the dates which were in the in the proposal of the SPECS project, and so far we stick to that. And but if the discussions also, the results of the discussions would be that it would be really valuable if we extend, or if we could include more start dates or so, I think we could talk about that.
I can probably comment. I mean, that the August and May start dates are the traditional seasonal forecast kind of evaluation start dates. So that I mean those are your start dates for the autumn and the summer seasons, and so that's why they were chosen. Obviously, a lot of research has come out and said that those aren't necessarily the best start dates to use, and it's a very valid question. But you're going to be fighting, of course, a trade-off between feasibility and computational feasibility, and obviously need. So.
I'm just going to say, as far as organizing these, I mean, there's already been existing runs, obviously, it'd be useful to evaluate, but there has been some amount of this done already. Bill Merrifield and our group did do this across several different hindcasting exercises, all started initialized at the beginning of every month going back to 1979, and it was useful exercise, but I didn't think there was a lot of new information that came out of that. There was new information beyond what we already learned in the individual exercises, so it's not a guarantee you're going to get a lot of great information out of these MIPS.
Just a quick question for people that are doing these runs. Is anyone actually running model output statistics? Like the GFDL model you said you're trying to correct for drift. Are people doing model output statistics, or there's not enough data, or are people doing reforecast type analyses? Is that... Right, so the operational centers are doing it, but maybe not, well, I don't know, others?
Yeah, so for the NMME, they ask for a specific set of hindcasts, which can then be used. I believe it's 1980 to 2010, something like that, so that the forecast can be detrended and bias corrected. Again, sea ice extent is kind of like this absolute value, and I know in our forecasting system where we force our data with MERA, and MERA has this particular issue in the springtime. It has a fixed sea ice albedo, and so we have a huge temperature bias, and so that's the reason why our forecasts go to crap in the summertime. But as I was looking at this, I was thinking, well, I could bias correct this and get a reasonable forecast, and then I was like, well, that's not a good idea. So I'm always a little bit concerned about doing this type of bias correction with the sea ice extent, and I'm wondering whether other people have ideas about that.
Rika may chime in, but CCSM in their decadal forecasts had the model, respond to shock in the initial conditions by going away from its normal mean state. So we wouldn't know how to bias correct that. And I'm curious if anyone has had that issue as well. And we don't understand it. It seems to go through some kind of oscillation where it drifts further away from its mean state. In fact, just as a Pan-Arctic average, the mean state's very good compared to what we were initializing. So strangely enough, it drifts away from reality.
Well, I think in that case, I mean, traditionally bias corrections are lead time dependent. So I mean, if it drifts in one direction originally, I mean, it doesn't really matter what happens. You bias correct for essentially the drift of over the hindcast period, no matter what it is. So solvable problem.
It turns out I can't count, so I noticed, Betsy corrected me, that was only 4 talks, not 5. Sorry about that. So Wisla, I'll have you come down and give the next talk, and maybe we'll take a pause again after another 3 or 4, since we have 6 more to do. Okay.
Okay, so this is a very brief presentation on our regional Arctic system modeling that a group of us has been involved for the past 7 years. The program is called the Regional Arctic System Model, and we believe that it's a very good tool to address some of the issues that this workshop is concerned. We think and argue that RASEM could be a good tool to resolve, understand processes and feedbacks that are currently underrepresented or not represented in the state-of-the-art ESMs. We believe that if we do processes and feedbacks better, we'll reduce uncertainty and improve prediction. The Andrew Roberts is here, and John Cassano, who is another PI on this project, was supposed to be here, but haven't seen him yet. And we have a whole RASM team, and has been supported by a number of agencies that are shown below. So why and what RASM can offer? We believe that by employing high resolution and focusing on the Arctic region, we can better resolve underrepresented or not resolved processes in the Arctic system, in individual components, as well as in the way that they are communicating. We believe that having a focused regional model will allow us to address some inadequacy of coupling channels between different system components, so coupling the sea ice to the atmosphere, sea ice to the ocean, and so forth. And the most interesting thing that we have been recently involved is the sensitivity to variable parameter space. I'll show some results, hopefully, in this brief presentation. The idea is that we have been using parameterizations of subgrid processes and coupling of subgrid feedbacks that were developed some years ago, and we keep increasing resolution and changing various model configurations. However, we have not explored this sensitivity to this variable parameter space. If we go from 100 kilometer to 10 kilometer grid cell in the sea ice, are the parameterization and parameters values that we have been using in the low resolution still good for the high resolution? And RASM is not a final solution. It's a middle solution to where we go with possibly global variable resolution models, such as, for example, Los Alamos MPAS or AVI modeling effort as well, where you can focus on the Arctic region and have a global grid. So the RASM wiring diagram as shown here. We have the atmospheric component, sea ice, ocean, and the land. All those are coupled through the with the flux coupler. The three components of this configuration are identical to the CSM 1.1, and except that those are regionalized components. We have atmospheric model WRF instead of CAM, and we're using land variable infiltration capacity model instead of CLM. We also have recently introduced the routing scheme that communicates the runoff from the land into the ocean to couple land to ocean as well. And we're working currently on dynamic vegetation and land ice to include into this model. The way we look at as RASM contributing to the sea ice outlook is that we can use either reanalysis or the output from Earth system models, and basically use RASM to dynamically downscale the solution at seasonal to interannual or decadal prediction, where within the Arctic we hope to resolve better those processes and feedbacks that might be important for the Arctic region for predicting sea ice. Here's a way that we think that we can proceed. Instead of doing individual data sets for data simulation like sea ice, SST, SAT, and so forth, we believe that the best way possibly, or one of the better way, would be to nudge the atmosphere to the observational state, such as reanalysis, for example, from ERA interim, and run this model in a hindcast up to the present and use the initial conditions from that state of the whole RASM system to run seasonal, interannual, and decadal prediction. I don't have a pointer, or maybe I do. Basically, there are red lines and blue lines. Those are a sea level pressure comparison for mid-January, March, April seasons. And basically, you can see with the nudging, we can have a very good comparison between the ERA interim and the model. This should be driving the rest of the system in a more physical way. And if we resolve processes and feedbacks within the system, we don't need to correct the sea ice and ocean and everything else. We always will be missing some kind of new additional observation. With this, if we have the process resolved, we hope to get the initial state as accurate as possible. Here's a good and bad news. With forcing, with the realistic forcing such as Core 2, the 30-year run you can see for September mean. The green contour is the 30-year mean ice extent from satellites, and the black contour end of the shading is our ice extent from the model. Those are 4 different experiments, and the bad news here is that I can represent the ice extent in the mean and individual years for September or March or any other ones quite realistically with this variable ice thickness distribution. So the bad news is observed sea ice extent is not sufficient constraint for climate models. If we will continue using the ice extent only as a constraint and quantify or qualify model performance and prediction, this is a big mistake because you can go between this state or that state and still argue that you have a perfect skill. So in terms of the model observations, we also would like to propose that there is additional requirements that coupled climate models need now in order to improve their representation of processes, constraining the simulations and validating the models. Not only the core variables such as temperature, salinity, or the ice concentration and extent, but we believe that we need to constrain model at a different level by looking at processes, fluxes, and energy budgets within the Arctic system. So from that perspective, we need to look at how the different feedbacks are represented in a model versus how they are actually occurring in the real world. So we need to observe feedbacks and fluxes, not only the state variables, to improve the coupled model performance in terms of representing those fluxes and representing the system in terms of, for example, total energy budget in the Arctic region. So I'm running out of time, of course. Our plans are to actually do dynamic downscaling with the output from the CSM, for example, for 21st centuries. We already have this capability to do the reanalysis for the boundary condition. We think that there are different ways with regional model to do ensemble generation. One of them is a traditional initial perturbed values. We can also do different boundary conditions for the regional model. And the last thing is that we believe that parameter sensitivity can be a source of a separate ensemble generation as well. I'm running out of time, so thank you very much.
Thanks very much, Wisla. I'm sure we'll have lots of questions during the pause after the next 2 speakers. So the next speaker is Xinlan Zhang. I'll cue up your talk from University of Washington. Take it away.
We have developed a numerical ensemble seasonal forecast system for Arctic sea ice. Well, the system is based on the Pan-Arctic Ice Ocean Modeling and Assimilation System, or PIAMAS, and the Marginal Ice Zone Modeling and Assimilation System, or MITSMAS. These models are coupled ice ocean models that can assimilate satellite ice concentration and SSE data. The forecast system is based on the assumption that the current climate is not fundamentally different from the recent past, even though the Arctic is changing rapidly. So based on this assumption, we can conduct seasonal forecast using recent observational or reanalysis forcing. For this forecast system, we stick to 7 ensemble members, each of which is driven by the NCEP-NCAR reanalysis forcing from one of the past 7 years. So the median of the 7 ensemble members is considered to be the outcome of the forecast. The system is aimed to obtain the best possible estimates of sea ice and ocean states for initial conditions for ensemble forecast. This means that we need to improve model physics and the data assimilation and do near real-time hindcasts to get the best possible initial conditions. The goal is to predict both the size and the shape of ice extent or ice edge location, as well as the spatial distribution of ice thickness. Of course, this goal is a very difficult goal. Now, this is PIAMAS and the MITSMAS grid configuration. The PIAMAS horizontal resolution is more evenly distributed for the Arctic basin, while MITSMAS is more focused on the Pacific sector of the Arctic Ocean with high resolution for the Chukchi, Beaufort, and Bering Seas. Now, this slide shows the ensemble forecast of September 2012 ice thickness and ice edge with and without the ice bridge and the electromagnetic ice thickness data to improve model ice field. And Julian has shown a similar figure that it was created by Ron. The forecast starts on June 1st. So the forecast range is 3 to 4 months. The white line is satellite observed ice edge, and the black line is the PIMAS predicted ice edge for September 2012. The prediction is based on the median of the 7 ensemble members. So the 7 individual ensemble members actually vary quite a bit, that reflecting the uncertainty of the prediction. Now, given that the ice bridge and the electromagnetic ice thickness data were connected mostly in March, so this data were used to improve PIMAS 12 category ice thickness distribution field on April 1st, following through optimal interpolation, following Lindsay et al. 2012. And then the model uses April 1st ice thickness distribution field as the initial conditions for continued handcast up to the end of May, followed by forecast starting on June 1st. As we can see, using the ice bridge and the electromagnetic ice thickness data, the model prediction of ice edge is improved quite a bit in this area compared to the forecast without the data assimilation. And overall, the predicted ice edge is not too far away from observed ice edge. But still, the model overestimated the ice extent for September 2012. The question is if we had the better data coverage in space and time in 2012 and use the data to improve model initial conditions, would the predicted ice edge get closer to, even closer to a reality and improve the overall estimate for the extent. Now this, the 2013 forecast is a very different story. They predicted that ice edge missed the target pretty bad in the Pacific sector as well as in the Atlantic sector, with and without using ice bridge and electromagnetic ice thickness data. And in fact, the use of ice thickness data makes things even a little bit worse in that area. So this is really a surprise. The question is why it's 2013 is just a peculiar year that is born harder to predict, given that many of us missed the mark in the September 2013 outlook. So it will be useful to pay special attention to those unusual years when most of the prediction would fall short. It will be interesting to shed some light on why that happens, what is unusual, if any, and how to make improvements. So the future plan. First of all, we will continue what we have been doing using reanalysis forcing for ensemble seasonal forecast. Meanwhile, we will team up with Muyin to explore the possible new ensemble seasonal forecast using the CFS atmospheric forcing to drive PIMAS. As Wanchi will tell you that the NCEP coupled forecast system has been routinely conducting ensemble seasonal forecast, and to predict the atmospheric data may be useful for driving PIMAS ice forecast. Muyin has been processing CFS forecast data, evaluating performance, and also interpolating data into PIMAS model grid. The plan is that the PIMAS will be first calibrated and validated using CFS reanalysis forcing or reforecast forcing in order to be adapted to the CFS forecast forcing. And after that, the actual forecast will be conducted and the forecast performance will be conducted, will be evaluated. Then also, we just heard that Richard mentioned that NASA is also doing the ensemble seasonal forecast. The atmospheric force may be also useful for drawing biomass. Yeah, finally, this is a movie showing a mid-mass hindcast and forecast of sea ice thickness and the prediction of ONR mid-array movements in 2014. In March, ONR set up 4 camps in the Balfour Sea with a bunch of instruments deployed. So this hindcast and forecast is meant to provide some ideas of how ice thickness would evolve and how the campus would drift in the next a few months. Note that each of the ONR mid campus has 7 ensemble drift predictions. So we can see that the drift predictions are quite scattered, reflecting the uncertainty of the prediction. Thanks.
Thanks, Jinlin. And next we have Ivan Sudakov, right? And excuse me for mispronouncing that, from University of Utah. I have to cue up your talk.
Okay. Thank you. So yeah, it will be an unusual talk for this workshop because I present here mathematics department at the University of Utah, and we have a great group for mathematics of sea ice. It's a quite important problem, and for mathematicians, for example, because a lot of interesting problems for us were coming from sea ice. For example, historically, the Stefan problem, it's a free boundary moving problem. It's coming from sea ice, and I don't know, sea ice is composite material. It's quite important in theoretical physics. And here we try to develop this, some mathematical and mathematical models of sea ice, which are quite important for climate prediction. And also I represent here MCRN, Mathematics and Climate Research Network, and here we developed some tipping points problem in the climate system. And when, I don't know, probably you may know, some years ago it was the big concept was introduced, tipping elements and tipping points in the climate system. Timothy Lanton was introduced this concept, and we can determine some tipping elements in the climate system, and these elements were quite important for the climate system. If you look at the climate system dynamical system, you can determine for these tipping elements so-called tipping points. And for example, tipping points, it's in mathematics bifurcation points, because the climate system can go through these tipping points from one state to another equilibrium state, and it's related to some catastrophic events. And when at MCRN we try to develop theory of tipping points, and especially I have some works related to permafrost methane emission, but here I want to show some interesting works related to sea ice albedo feedback. And the main problem in this area, because we haven't strong contact with field researchers, we need some important data. So, for example, look at this. For example, a really interesting phenomena in the Arctic climate system was introduced by Hohenegger and al. And from imaging analysis, they found some interesting phenomena for melt ponds. Like melt ponds, the structure of melt ponds is so non-linear structure, and it's starting from a pond, and it's going to the fractal structure. And if you can measure geometry of melt ponds of this system, like a fractal system, we can estimate fractal dimension. And in this system, it's going from, if you want to look at fractal dimension, it's going from 1 to 2, and it has a transition at this point. It looks like phase transition in theoretical physics. We have a lot of models. And of course, this phenomenon, non-linear effects in melt ponds, it's so interesting for investigation. Like, it's not only like our professional interest, because we want to develop this, I don't know, theoretical physical models for melt ponds. It's also interesting for the tipping points, and I'll show later how it can be related. So, and the main problem, we need to build a special model which can describe this transition. It's so-called, we applied so-called the random field Ising model. The Ising model, it's coming from theoretical physics. It's related to ferromagnetics, and it's an interesting thing because electron in any material, for example, it has a properties. It has an electronic magnetic moment, and it can be like spin up and spin down. And the same thing we can describe melt ponds, because ice, it can be like, it has properties like -1, it's like spin down, and 1, it's spin up, it's just water. And this model, Ising model, originally, it's all materials, they can have ferromagnetic properties under influence on magnetization, in external magnetic fields. And here we want to apply this model to melt ponds, and Ising model can describe ice topography, and we used it here like ice topography and horizontal heat transfer. And this model, it can predict transition like in nature, you've seen right now, and we can predict this critical point, but the main view, but it's like modeling data, but now it's real observational data, and we haven't agreements between this data, because sea ice topography, it's quite, it's no data related to sea ice topography like spatial distribution of sea ice topography, and which phenomena can be related to prediction tipping points, because previous model for sea ice albedo feedback, they can show just two states, like snowball and like ice-free ocean, and it's like two tipping points, and which is so critical for the climate system. But if we want to incorporate to simple climate models, like if we can incorporate melt pond, we can get a new type of tipping points which is related to sea ice albedo feedback. And the main conclusion, it was like melt ponds, they can stabilize the albedo, and probably it can, and it's a good way for prediction tipping points. But anyway, and here we have we need a lot of external information from observation, like melt pond geometry, radius, melt ponds radius distribution, spatial distributions, sea ice topography, and so on. But anyway, if you hear we discuss about sea ice prediction, and the main reason for stakeholders, for society, we really want to know what is the tipping point for the climate system and how we can predict these tipping points. And this model were quite important. And unfortunately, right now we haven't strong data for this model, and I hope, it's a so strong collaboration between field researcher and mathematician that can help to develop these models, and we can say exactly something about tipping points related to sea ice albedo feedback. Thank you.
Thanks, Ivan. Do you want to take one quick question? Is there? Yes, actually. Trudy, do you want to run back there? Come back here. You stopped 30 seconds before your time was up.
It's not exactly a question, but if you're looking for data, because melt pond characteristics are extremely different between first-year ice, second-year ice, and multi-year ice, the way they form. Michelle Johnston, I don't know if you've heard her name. She works at the National Research Council in Canada. She's produced a really nice book on multi-year ice characteristics, and it's mainly meant for observers on ships so that they can identify one type of ice from another. But with each example in her book, she has all the melt pond characteristics that you would probably be interested in, so size, distribution, that type of things. So I can either put you in touch with her or I'll send you a copy of her book if you're interested.
Yeah, okay, thank you. But I want to emphasize that we need to get some unusual data, like yeah, how you can present some, for example, like sea ice topography, but it's like temporal distribution of sea ice topography, and we need like a spatial distribution for sea ice topography, for example, and horizontal heat transfer, because field researchers usually measure like a vertical heat transfer. It's not good for these models. Yeah, it's a main problem.
Well, once again, we're going to take a pause because we just have 3 talks left and we have about 45 minutes, so we have time for some discussion. Am I right about that? Great. Okay. So we wanted to also have discussion, not just about activities your group is doing, but how the Outlook could improve and address some of your needs. So if that could be an element of the discussion, that would be very useful. Okay, Vladimir?
Thanks, Cecilia. I would like to pick up on the talk that Wislav gave. And this is my usual talk, actually, but you know, this is a new group, so I think it should work. So in the stratospheric research under the World Climate Research Program, there was a project which was called Climate Chemistry Model Validation. The idea was to help prediction of the stratospheric ozone layer, and of course there was not a lot of data. So people were trying to focus on processes. They would imagine a physical picture of certain processes and how this would be represented in models, and they would derive certain constraints that they could implement in models based on available data. And this was a very fruitful approach and the second generation of this project, which is called CCMVAL2, came up with much narrower clouds of predictions, because the first generation of models used for stratospheric ozone prediction were basically all over the place because of the unresolved constraints in models. So I think this is a very useful philosophical approach, and what Wislav was proposing was very important. But how you define these processes is also incredibly important. It should be defined probably not in terms of parameters of certain schemes, but in terms of sequences of physical processes that depend on each other. And how you do this will probably determine the future of your business. So I think this needs to be discussed in more detail. Thank you.
I had a question for the first speaker as well, and I guess out to the general public as well. I mean, you discussed the importance of closing the energy flux or the flux balance, and I agree that's a very admirable thing to do. But what are we going to validate against? I mean, coming from the ocean synthesis community, I mean, it's very clear that, I mean, we have flux buoy measurements, we have flux measurements, or field measurements, but they're not necessarily representative. We have the flux estimates from the atmospheric analysis, but they're wrong. And so it's going to take we need really a whole field program and a whole modeling program to address this problem. I mean, it's probably even going to be doubly difficult from the aspects of going through the ice and everything. So please comment on it.
So I didn't mean to say it's going to be easy. But I think there's a deeper issue here than just how easy or whether we want to do it. We are struggling with reducing the uncertainty, and the classical picture from Julien's paper, the CMIP 5 compared to CMIP 3 has increased spread in the Arctic. We're not making progress. So if we want to continue that way forever, fine. If we want to move forward, make progress, again, it's not going to be easy, but maybe we need a number of field campaigns, very coordinated, talking to each other, and actually involving modelers from the very beginning.
Well, more data is, of course, always good, but it's not like that there aren't any data around. There was an experiment called SHIBA that measured the flux balance. Many of us were involved, and I think if we can get close to what we have, we would have made progress. So just want to mention that.
I have a question for Rim, right? Is that how you say it? Okay. You showed that your model that had higher resolution did a better job of validating the mean state better compared to observations, and you, I think, concluded for the most part that it was better in prediction. But then when you showed these figures that had a lead time versus September forecast, it wasn't as good as the other. Do you have a comment on that? Like, and you didn't have to de-drift it, so it had some advantages. Do you have any ideas about why that is?
Yeah, we did de-drift it. I say as was mentioned, all these forecasts are always bias correct because they do drift, even if the drift is much smaller. So there is a lead-dependent climatology that is removed. So what I was surprised is that there is not much influence actually. It's not better; it's similar. It's about similar, except at longer lead time. So at shorter lead time, it's about the same. So.
Your message then that it isn't an issue so much to actually make your models perfect as to learn how to tackle that problem of de-drifting or bias correcting.
The problem of bias correcting, for me, it's like we remove a constant climatology, a given climatology. So you're going to assume that your drift is stationary in time, which it's not. So it's another problem here that I didn't discuss. But what I wanted to point, and it was a bit of a provocative message, is even with a much better model, it's not necessarily that you're going to get like much improved forecasts right away for this lead time. I don't know whether that will hold in other forecast systems. It will be interesting to see. But I only showed also sea ice extent. And what you see if you look more regionally, there are more differences, of course. And so the higher resolution model does better, for example, in the Barents Sea in March. And so maybe looking at extent is also not the only thing to look at. But it points to the importance of initial conditions to me.
Hi, yeah, my question was for Jinlun, and I guess Ron as well. So you showed the improvements potentially by assimilating some of this IceBridge data. So is your idea that the IceBridge data would be better than assimilating some of the satellite thickness data because it's more accurate despite the problems with the spatially sparseness of the data? So, by having this accurate IceBridge thickness, that's a potentially better thickness assimilating product than the potentially quite uncertain but pan-Arctic altimeter data sets.
Well, the satellite thickness data set would be tremendous if we could assimilate it, and it's a brand new data set. At this point, I guess I don't have a whole lot of confidence in what's been published is still under development, and maybe we shouldn't rush it. The only actual fields I've seen, numerical fields, were some that Stefan Hendricks put out on the web last fall. I'm not sure where the rest of the data is. And those data, I commend them for putting the data out there. But it's a work in progress. And I want to give them some time to get it right. But you're right. If we could use the satellite data, that would be an excellent way to initialize the forecast.
As Ron said, that satellite eye thickness data would be very valuable, that's for sure. But the ice bridge data is particularly valuable because it provides a thickness distribution fields for you. And so for PyMass and MISMAS, you do need eye thickness distribution, the PDF fields. So that would be a lot easier. Otherwise, if you provide a mean eye thickness, and we don't know how to do it. We have to make a lot of assumptions about how to use the mean thickness field.
Just a comment on the data from Stefan Hendricks, the cryosat data you are talking about, right? So cryosat data are available for thick eyes, about 1 meter or so. But we are at the moment using SMOS data, which are good for eye thickness below a half meter, with a reasonable error uncertainty. I will show tomorrow some slides. We are using SNOW as well from the University of Bremen. And they compared the data with NASA ice-bridge data. And on level eyes, the error is about 6 centimeters. For multi-year eyes, it's much larger.
Okay, Jim, you get the last word, and then we'll take the next talk.
A quick one, just commend the number of modeling groups that are here, and I know there's some other modeling groups as well. This was quite a bit different from when we started out, and one of the takeaways from this morning was to move away from just looking at the expected value trend line only, and I think the only way to do that is with ensemble forcing runs with the models. So I would hope perhaps in the discussion tomorrow we can address some of that, and the modelers would be willing to make multiple runs.
Thanks, Jim.
Maybe a last comment. I was worried this morning when I saw that the median prediction is on the trend, which is for me fine, but the range is most of the time not as wide as what we would expect. So there are realizations in the real world that fall outside of this envelope of prediction from the sea ice outlook. So I think that one of the next challenge also is to improve the way we can characterize the uncertainty of the predictions. And in the case of modeling, that I know best, it could mean to perturb the initial conditions, the forcing, and the parameters, all three at the same time. We could end up with a wide distribution of possible September ice extent, but I would prefer to have at least the actual realization into this envelope.
Yeah, that follows the intent of the outlook, and I think that's exactly where we were. I'd like to see a much wider spread before we try and narrow things down.
Good afternoon, everyone. My name is Arnold Song. I'm a researcher at the Cold Regions Research and Engineering Lab in Hanover, New Hampshire. And I'm going to talk to you today about our sea ice model that treats sea ice as a collection of relatively small pieces of ice. And we see this model as sort of a complement to the continuum modeling that's been going on, and as a high resolution test bed for examining small scale and fine scale processes. So why would we want to model ice as a discrete medium? Well, looking at these images of the SAR image of a region that's about 15 kilometers by 17 kilometers, and the images of pancake ice and Nilas rafting, that you know, it naturally lends itself to a discrete description. Also, I'd argue that as the resolution of continuum models continue to increase, they're going to bump up against the validity of the continuum assumption, where, you know, in regions such as the marginal ice zone, where the granularity may be within 1 to 2 orders of magnitude of grid cell resolution. So we have to ask ourselves about mechanical and thermodynamic equivalence of our simulations in the physical system that we're trying to model. So I just, sorry. So I just presented, this is a little simple kind of illustration of what I mean by mechanical equivalence. Here we have 2 ice configurations that have identical ice concentrations. So, you know, we have a large monolithic piece of ice and to the right a collection of smaller flows. So, subject to the same compressive and shear stresses, the strain fields are going to be drastically different for these 2 ice configurations. So we can account for this in a continuum model by parameterizing this behavior based on, you know, something like ice concentration or a size distribution. But what about, you know, cases where we have a network of cracks that are propagated across a piece of ice, or, you know, a non-uniform thickness distribution? So, and the same goes for the thermodynamics. I mean, if we consider melting, for the same energy input, the system composed of the small flows will melt out faster than the large flow due to the surface area to volume ratio being approximately 20 times higher. Well, for that configuration that I was showing before, if you have if the radius is 10 times smaller than the large flow. So now we're not saying that we can compete with continuum models, and you know, it'd be silly for us if we were not computationally efficient to be able to do something like that. But I think what we bring to the table is the ability to model finer scale processes that, because we can explicitly model discontinuous states. So we mathematically describe the ice as a collection of small ice particles, and where the large flows are a group of these particles that are glued together with ice bonds. And the dynamics of these particles are driven by wind and water stresses, and also due to stresses due to particle interaction. Cracks can, in our model, cracks can heal and propagate. Ridges can form as ice pieces are pushed together. And also ice can grow and melt in the vertical direction according to a 1D thermodynamical model. So this work has been around for a little while. You know, it kind of, I'd say that it's gone into, it went into a bit of a holding period for the maybe the better part of the past decade. But but this has been used to examine pressure ridging, wave ice interaction, onshore pileup, and recently it's been used a lot for estimating ice forces on ships and structures. And this is just an example of, whoops. Uh-oh. Well, this may not play. Yeah. Here we go. So this is just an example of a basin scale simulation that Mark did, and comparing the path of the Shiba camp path, drift path, with simulated drift path, which is in green. It ends up drifting off towards Russia near the end of the simulation. But you can see the, you know, it just demonstrates the opening up. The opening up of leads. It's hard to, you can't see it in this, but it's really hard to see. But then there's the formation of ridges and those details. So, oops. So moving forward, we're focusing on the assimilation of remote sensing data and weather forecast data in our models to generate short-term forecasts of ice conditions. And then, so I'll just show just a short animation of a preliminary result where the initial ice configuration was determined from a SAR image. And a couple of things to point out with that animation was the breaking and then the subsequent jamming of a large ice piece. So this is just a, it's kind of a non-realistic test case, but it just kind of shows that what, I guess the working parts. One last thing is that we have a validation experiment planned for this summer where we're going to task a time series of SAR images in the Beaufort Sea and, to use as a case study data set.
I mean, this, as you said before, it's not really realistic to do this at a pan-Arctic scale, but I mean, are you planning to maybe sort of apply this to, say, the Canadian archipelago, the Northwest Passage, and, that kind of scale? Because, GCMs are not practical for that small scale, but I think this could be quite useful for that.
Yeah, I mean, so our sort of target, I guess, scale is, and this is just a rough kind of number that we're using as a sort of a target is, regions that are on the order of, say, 50 kilometers, and with resolution of on the order of, say, 10 meters.
So one question about noise in the system. I know some work from John Wetlaufer, and he proved that in such system like where CI is like granular medium, it has a noise, and noise can influence on dynamics of the system. What about noise?
Sure. Yeah. I mean, there's definitely, I guess, little numerical tricks that we'd have to play. In terms of that, we in our soil models that we what we end up doing is shrinking the time step to be very small, you can't have your system can't be too stiff, or else things can go unstable very quickly. I don't know if that answers your question.
Thanks, Arnold. You guys can talk more about that later, perhaps. The next speaker is Barbara Brown. She's from NCAR.
Okay, so this is going to be really something completely different for those of you like Monty Python. It won't be that funny, though, I'm afraid. So I'm from NCAR, and I work in a group, lead a group that's called the Joint Numerical Testbed Program, and the focus of our group is the testing and evaluation of numerical weather prediction models, and also starting to look at climate models, as well as looking at extreme events and other kinds of statistical applications in weather and climate. So I have two colleagues here, Tressa Fowler and Randy Bullock, who are also working on this effort. And I think that, mainly we have worked on weather prediction, but I think some of the ideas that come from weather prediction can be very useful, both in climate and in looking at sea ice, and especially for seasonal predictions. So the purpose of this talk is just to give an overview of some ideas around verification or validation, whichever one you want to call it, and why we do that, and some tools and capabilities that exist, and also some new ideas and some things that might actually be pretty useful for sea ice evaluation, I think, but they have not been used yet as far as I know. So why do we do verification or validation? We want to monitor performance, we want to improve forecasts, we want to do model intercomparisons, as we've been talking about earlier today, and thereby find ways to improve the forecasts. We also want to communicate meaningful information to users, and I think that's a really key part of why we want to do these kinds of evaluations. We've talked some about the need for uncertainty information, and I think uncertainty information can be derived from the evaluations as well as including it directly through ensemble prediction and other methods. So thinking about doing verification requires also thinking about who the users are, whether they be scientists or shipping groups or oil platform people who are managing oil platforms. So we need approaches that can do all of these things, and it turns out we need different approaches for different purposes and different types of forecasts, of course. So I think the idea of looking at a wide variety of approaches is really valuable, and I think at this stage of where the sea ice prediction project is a good time to start thinking about that, broadening the way we look at these things beyond just root mean squared error and anomaly correlation if possible. So different purposes, monitoring, we would maybe just use basic, easy to understand metrics like root mean squared error. For forecast improvement, we want to look at things that are more diagnostic and dig deeper into some of the processes and characteristics. For users, we also want to have some diagnostic approaches, but we also need to think about things that are relevant for those particular users. Perhaps ice existing in a particular bay or something like that. Or the timing of certain conditions, as we heard, is one of the important predictor variables. So different types of forecasts also influence the kinds of ways that we can look at it. We have approaches that have been developed for continuous statistics, such as root mean squared error, categorical if we're really concerned about exceedance of some event, so exceedance of or lack of ice at a certain level. We would want to look at categorical approaches. And then there are a lot of methods that are developed for directly looking at probabilistic methods that really should be looked at as this community moves toward ensemble prediction and really taking advantage of the ensembles to characterize that uncertainty rather than just looking at the mean or the median. And then temporal characteristics are also important, looking at how things evolve through time and being able to evaluate those. There are methods also available for those. And then finally, there are a number of new methods, and I'll talk a little more about this, for evaluating the spatial characteristics rather than just looking at grid point by grid point, actually characterizing, for example, where the sea ice is or where the concentrations of the different concentrations are. And I think some of those methods might have some big benefits here. I wanted to mention that there are community tools for doing these kinds of evaluations. They were originally developed for looking at weather forecasts, but they're also usable for for climate forecasts and pretty much any other kind of forecast that can be put in the right format. So it includes a lot of the traditional approaches, but it also includes a lot of the new methods, such as these spatial methods. It gives confidence intervals so you can actually make some rational decisions about whether one model is better than another model. And it's currently completely supported to the community. It's freely available and used around the world. So it includes regular tutorials as well as email help. So just wanted to mention that as a resource for any of you who are looking for possibly some kind of capability like that. So now I want to talk about why spatial verification is important and thinking about things more spatially rather than grid point by grid point. This is just a really mocked up example showing what we call in the weather community the double penalty problem, which is the case where we might have a prediction of could be, in this case, precipitation most likely, where we have the first example over there in the upper left that we have exactly the right amount of precipitation or whatever the element is, but it's just displaced a little bit. It's the right shape and the right size and everything. And then we have a second example where we have a low resolution forecast that has much bigger and lower, the intensity is not correct and so on. And then we have the lower left one, which actually scores the same scores as the one in the upper left, but it actually doesn't look like nearly as good of a forecast. So what we see with this example is the root mean squared error is much bigger for the case where there's just a small displacement and the size and intensity are correct, and probably is for the most part a much more useful forecast. So with the traditional scores like root mean squared error, we don't have a way to tell really what's going on in the forecast, what really went wrong. We just know it's a bad forecast. It doesn't tell us that kind of information. So the new spatial methods give us some ways around that. This is another precipitation example, forecast and observed. You can see they look fairly similar to each other. But if we do grid-to-grid comparisons of these forecasts, then we get really poor results. But if you look at it, you can see some areas that look fairly similar between the two between the forecast and the observed areas. And that's completely ignored by the traditional verification. So I think the important thing, though, is that the spatial methods can identify particular features of interest. And there are a variety of spatial methods that have been developed, neighborhood, object-based, scale separation, field deformation. I don't have time to explain all of them today. I want to show an example using an object-based method, basically for the same example I just showed you, where this method for object-based diagnostic evaluation uses an object-based approach to characterize the precipitation. And overall, it says that we have a pretty good forecast, even though traditionally it would be poor. So I think these tools exist and could be used for time series as well as for spatial forecast evaluation of sea ice and so on, and provide good diagnostic information. So I'm done, but I want to mention that I'm not going to be here tomorrow, but my colleagues Tressa and Randy will be participating in the breakout group. So if there are questions, and there's some resources.
Thanks, Barbara. We'll take questions at the end. Okay, thank you. A lot of food for thought. Matthew Chevalier is next, and I can't remember if it's a PowerPoint. I think so. Yeah, there it is.
Last speaker?
You are. You're lucky, because then there will be fresh minds to ask you questions.
Okay, so I'm a little ashamed because I'm just the last speaker, and I will talk after lots of very interesting talks. So we have to make a presentation just then about advancing predictability, thinking outside of the box. I think we already are outside of the box with some of the presentation that will be done just before me. Okay, so I'm from Météo France. My name is Mathieu, but if you have trouble to pronounce it, just call me Matt. And from January on, I am responsible for this activity on seasonal forecasting of sea ice, more generally on the marine environment in the Arctic, at CNRM, which is the research center of Météo France. So the presentation will be more an advertisement of all the activities we did, then the activities we planned, and some examples of things just to think about during the break. Okay, so first the season forecast. We did all the work is based on the Hindcast we did with our model, which is CNRM CM5. The couple models, the CMIP5 model of CNRM, which is about 1 degree resolution, horizontal resolution. So we had the start dates May 1st, August 1st, and November 1st. So Drew told you why. And all the skills we had that were very encouraging about with the Hindcast are described in our paper of 2013 in Journal of Climate. So they are very encouraging. So now I'm not alone. I'm not alone now that I'm back at Météo France after my PhD. We have Virginie, which is spending half her time as a postdoc in Météo France, so in the framework of the SPECS program. And so we are able to do lots of interesting things. One of this one was a case study of 2012, which was published in BAMS last year. And so one one of the motivation of this work is to now have the sea ice model in the future Météo France operational seasonal forecast system, because before I did my PhD, there was no sea ice in the seasonal forecast in Météo France. Okay, now just to mention also, we had this effort on decadal hindcasts based on the hindcasts we did for CMIP 5 in collaboration with Fairfax, Christophe Cassou and all those folks. So this is Agathe Germ, who spent 2 years with us, who wrote this paper that has just been accepted on regional skills and regional predictability that we could investigate using this hindcast. So I recommend you to read this paper. Now I wanted to mention that a large part of this work has been done with collaboration with stakeholders. I would say just one stakeholder, basically. This one was Total Oil and Gas Company, which had expressed some interest in seasonal forecasting in the Barents Sea and the Kara Sea. And so this has motivated part of my work, basically studying winter sea ice predictions in the Barents Sea. I'm still preparing a paper on that subject. Then we also have activities on sea ice ocean development. So it's not really related on seasonal forecast, but it's also something that motivated our interest in that subject. We developed our own sea ice model, which is called Gelato. Yes, it could just have been only a sea ice model called Gelato. And so this is basically a model which has the EVP, the dynamics, and also, no, it's not ITP, it's ITD, salinity, snow, and also interactive melt ponds. The father of Gelato is David Salasimelia, and I'm kind of godfather, would say, because I'm younger. I just took the development on Gelato in charge, just arriving at CNM. And to make the development, we constituted like a validation suite based mainly on the CI thickness climate data record from Ron Lindsay. Thank you. It was a very useful tool. And also, we had a collaboration for now 3 years with a French guy which works at NASA and passed us the personalized bridge data. Okay, now future works. We want to continue to build up on a regional approach, mainly starting to study other predictants as the dates of ice clearance or ice freeze up, and also continue working on the winter predictions. So here I'm outside of the box still because I'm not talking about September predictions. I think so. What we learned about with our collaboration with stakeholders is that they are also interested in prediction of the March or April sea ice thickness, the ice extent. Okay, now then still with our collaboration with Virginie in IC3, we want to work on multi-model contribution to the next sea ice outlooks. So basically based first on our 2 models, but maybe on adding other models if other people are interested. And another thing I wanted to mention is that we want to extend our expertise in sea ice forecasting by also including biogeochemistry dimension. I would say that now the next generation of dynamics of coupled model will have also their Earth system model clones, and so we are working on that, on such a model using NEMO and Pisces biogeochemistry model. And we have a colleague who did this PhD on how predictable was the marine biogeochemistry, and so we are motivated to try to build up, so to mix all the approaches to see if in the marginal ice zone, for example, or the subarctic seas, we could have an added value of having a dynamics sea ice and also a good representation of the marine biogeochemistry called processes. We have a master student starting this year. So just last point before some beautiful pictures. We continue also working on building a verification suite of data based on observation. And I would mention, but I will talk more about it during the advancing predictability session. I'm also coordinating with people in Météo France, in Mercator and Environnement Canada. Environnement Canada is Greg Smith. an intercomparison of the sea ice cover represented in the ocean sea ice reanalysis, the global one. Okay, so it's something that will be submitted in July. And finally, some work about shorter lead times, but we can talk about it later. So just a first plot of what could be an output of our seasonal forecast. For example, here is in the hindcast of my model initialized on May 1st in 2008. You have here the date of ice clearance. So when the concentration goes lower than 25%. So basically here it's May 1st. September is near here, and you see there's maybe some useful information, for example, using here the mean or the max or the mean or the minimum. And you see that we can have some, for example, here using the maximum, so maximum date of ice clearance, we could have information on the possibility of having open lanes of open shipping routes, for example, here in the Northern Sea route in 2008. I won't talk about it much. And here's what I produced for the collaboration with Total. So in the Barents Sea, that it's good to have the size, so the magnitude of the sea ice extent we forecast, but also it's interesting to have the shape of the sea ice age. And here I have two examples to show that it can be possible also with a model with a 1 degree resolution. And finally, we are not in the Arctic anymore now. It's the tropical Pacific. Just to show you the result from my colleague using this hindcast with the marine biogeochemistry. Here you have the correlation of the net productivity, primary productivity for year 2 to 5. And you see that the skill score, so correlation here is very high. And what is interesting is that it corresponds to the fishing areas of the period over which we did the hindcast. But also what is interesting is that these hindcasts are only initialized through SST nudging. There is no assimilation of, for example, the primary productivity. So it's possible. So you can ask me more questions because I think I'm running out of time. But what we think is that because sea ice seems to control, for example, the marine biogeochemistry in the Arctic, there can be, if we have the right representation of the physics and biophysics feedbacks in this region by improving the model, we could have some benefit in the sea ice forecast and also forecast of the marine biogeochemistry. So thank you very much.
Okay, we have time, about 5 minutes, for questions all around. And anyone want to start off with any question for any of the last 3 speakers?
Okay, great. I was really happy to see that you're looking at timing and winter forecasts and spring forecasts. For the winter forecast, have you also thought about not just the marginal ice zone, but within the pack itself? Because I found myself the last few years being faced by people doing either science projects or naval exercises or expeditions in the Arctic looking for an outlook. What is the ice going to be like in February and March when I'm going between the Canadian Arctic and the North Pole, or I'm working in this area of the...
So I had a look at it, but more in a potential predictability mode, because there is no observation of, no verification data for sea ice thickness, something like that. But also tried to look at if we could have some added value with the forecast of the ice thickness distribution, because it's a model which has an ice thickness distribution, the one we use. And the problem is I met is the problem of metrics. How can we just how can we evaluate this kind of hindcast of high thickness distribution? So maybe it would be interesting to talk about it if you had some clue of what is the information that's relevant and what I should look at.
So you mentioned that Total were interested in March and April forecasts.
The question is, why is that, and are we too focused on the September minimum?
Why are you, the question?
Why are they interested?
Why isn't
and are we too focused on the September minimum?
So the first question is why they are interested in it is because actually the one of the field here was in the marginalized zone. So and then the question was not about September because there was no sea ice, but the thing is that they were just near a place where there are some years that the ice age was far north and some years when they were in the middle of very old ice. So this was their interest. Then they have another issue. It was about an harbor from there where they had the ships had to make some exportations, and then it was a question of forecasting if the condition near the shore. So this is basically the case for the Kara Sea. Now this is a question I ask: why are we focusing on the September predictions? And this is a real question. Maybe we have to listen to some stakeholders that are more interesting in the marginalized zone. But okay, just wanted through the discussion here.
Thanks. I've got a question both for Barbara and you and anybody else here that might know the answer to this. I have a background in industrial weather forecasting, so I forecast for the oil industry, both in Australia and in Britain. And typically, the oil industry is very interested in some very specific parameters. For example, liquid natural gas tankers can only dock in shallow water ports when there's not a significant swell above 18 seconds. Or in the West Shetland Basin, some oil rigs that aren't anchored to the seafloor in any way are affected by 22-second swells or greater. So far, we've heard about sea ice thickness and concentration, but I'd like someone in an operational centre or anyone else here that might know if there are some very specific numbers that the oil industry is interested in. For example, internal stress of sea ice, thickness, concentration combined, rather than just a seasonal forecast where we're giving them an ice-free or non-ice-free area.
Anyone want to tackle that? That's a really good point. I guess, yeah? Do you want to say that first? And then
I know one of the kind of operational concerns, partly for natural gas or natural resources extraction in the Arctic, also for fishing and other marine resources, looking at freeze-up dates. So when there's going to be ice cover, especially kind of flash freeze events, not necessarily the regional area, but like within a pretty specific spot.
Well, I think we better stop, actually, sorry, Ed, because the webcasting needs to switch over for the seminar that starts at 3:30, and that takes a little bit of time. But I will take one opportunity to say something myself, which is, I just thought it was really exciting to hear about potential metrics that don't just look at the Pan-Arctic, but also tackle this regional challenge that we have of looking at a certain point and asking, is there supposed to be sea ice here? And the validation says no, and we feel like we're a failure, but how we could actually quantify that in a way where if we're close, we get some value, or we don't fail entirely. So we need to think more about that, I think, as we move to more regional methods. So I guess I have one question just before we break, and that is, we've been having we are having a half-hour break, and we did this morning. Is that better than having more time for discussion in the general room, or would you rather have shorter breaks and more time for discussion? I guess I'll say, better ask, raise of hands. Who would prefer to have the 30-minute break in shorter time? Okay. And then who would prefer to have less break and more time in plenary discussion? Okay. Well, I guess we'll stay with what we have. Thank you for voting. And we'll be back here at 3:30 for Ed Hawkins' seminar for all of CGD with us.